Well, once I see her slides, I can say the title of her talk.
Wait just a second. Great.
She'll be telling us about energy reflection and transmission and two-dimensional holographic interfaces. Shira, please take it away.
All right, so thanks a lot, Kristen. So let me start by thanking the organizers for organizing such a wonderful conference and for giving me the opportunity to speak in it. So today I'm going to talk about a paper which we wrote together with the Costas Pakas and Giuseppe Policastro from École Normale and Dongsheng Ge, that is now a new postdoc in Warsaw, was a student in École Normale. And in this paper, we were trying to study some universal properties of energy reflection and transmission from what is known as conformal interfaces in 2 dimensions using a very simple holographic model. So that's what I'm going to tell you about. Please feel free to stop me at any time. I'm always very happy for interruptions and to answer questions, or if I cannot answer, then I can answer later, maybe in the discussion session. So that's going to be the outline of my talk. I'm going to start by telling you a little bit about conformal interfaces in 2 dimensions, what is so special about them. Then I will move to the second part, which will be describing the holographic model. So this is a description of a very simple bottom-up holographic model of an interface, which is modeled using a codimensional 1 brane in the bulk. And that's the model that I will use to study these reflection and transmissions in holography. And the rest of the talk, which will be the largest part, will be devoted to explaining our result about energy reflection and transmission in this particular model and what we can learn from it. So first thing first, I'm going to start with some background about 2-dimensional conformal interfaces. So this, I assume you all know, interfaces are codimension 1 extended objects which split the system into 2 parts. So for example, in 3 dimensions, they are in 3+1 dimensions, there are 2-dimensional surfaces on every given time slice, which split the system into 2 parts. And in 1 dimension, these are simply impurities that divide my system to 2 lines at every given instance of time. Now, as usual, there is much more that we can do when we have more symmetry. And in particular, here I will focus on a particular kind of interfaces, which is conformal interfaces, those that split 2 conformal systems, that's 2 critical systems, and preserve a large subgroup of the conformal symmetry. So in particular, in 2 dimensions, these are impurities which preserve as much as possible from the 2-dimensional conformal symmetry, which is already very large. That is 1 copy of the Virasoro algebra. And I should mention that conformal interfaces are relevant in nature. They appear in various physical systems, for example, junctions of quantum wires, surface and line defects in 2 and 3-dimensional Ising model. And we also meet them very often in string theory and in holography in various contexts, so they are of great interest. So let me go back to the picture that we very often work with, adding back the time to my system. So a 1+1 dimensional interface, dividing a CFT left and a CFT right, so 2 systems, which are each one of them is critical. And the interface that I will consider is running along the time direction. So it's at a fixed position running along the time direction. Now, it turns out that this interface, of course, breaks some of the symmetry. We see it immediately. We used to have translations along the X direction, but we don't have them anymore. But more generally, it preserves half of the symmetry. It preserves Virasoro generators which do not displace the interface, which are generated by some of the LNs and L bar Ns. For example, translation along the time direction would be one of them. And those generators that remain have conserved charges. So in particular, translations along the time direction implies energy conservation. It means that TXT component of the stress tensor is continuous when crossing the interface. And when expressed in terms of the left and right stress tensor, it basically tells me this matching condition of stress tensor on the left and stress tensor on the right. T minus T bar is T minus T bar. Before and after the interface, it's the same. All right, for those of you who have worked with defect CFTs in higher dimensions, you know that the spectrum of defect operators usually contains a primary operator, which is known as the displacement, whose role in the game is to displace the defect inside correlation functions. So in 2D, it turns out that the displacement is not an independent operator, but it's in fact related to the stress tensors of the theory by the following relation. All right. Now, as I said, since we have quite a lot of symmetry, although not as much as we used to have when the theory was really conformal, we can fix a lot of the properties of the theory. In particular, for example, two-point functions of the stress tensor are completely fixed by the conformal symmetry. So that's what we are used to from CFTs, that the correlation functions of two left stress tensor or two right stress tensor is fixed by the central charge, C left or C right. In the case of the defect, appears a new coefficient in the left-right correlations, which is basically, I mean, in a very similar way that it appears the central charge in correlations of left stress tensors, appears a new coefficient, which is, I will call it C left right, is characterizing the connection between the two sides, the left and the right CFT, and it will basically be the star of the play. So this C left right will appear everywhere. It's just one number, but it characterizes a lot of the behavior. And then one last comment is that very similar to what happens for boundaries, there is some kind of mirroring effect. So TT bar correlation functions will not vanish, but they will be fixed by, say, C left minus C left right. You can already kind of see that what happens here is that if I perturb something on the left, the transmission to the right will depend on this C left right, and what is reflected back will depend on the difference of the C left minus C left right. Okay, anyway, I can also fix stress tensor 3-point functions by the same coefficients, apparently, it turns out. And I didn't write all of them here, but I wrote some typical ones. All the other ones are obtained by replacing left to right or Z to Z bar. But you can see that again, this C left right, and difference makes an appearance. Now, 4-point functions, on the other hand, already depends on cross ratios. They depend on the details of the theory. So that's something that breaks down in the defect case compared to a boundary case or a usual CFT case where all the correlation functions of the stress tensor are fixed. Here it's not true. Once you get to the 4-point functions, things are no longer fixed. All right, so now I'm going to describe this quantity that I'm interested in, which is the result of a scattering experiment. And the idea is that I would like to send an incident wave towards the interface that will hit it at a certain value of the time. And a portion of it will be transmitted, a portion of it will be reflected. To characterize the outcome of this scattering experiment, I define two coefficients. One is the transmission coefficient, which is simply the transmitted energy over the incident energy. And the other one is the reflected energy over the incident energy. They should sum to 1. And in general, the system is not symmetric, so the left and right CFT don't have to be the same, and so the outcome of a scattering experiment doesn't actually have to be symmetric. It could depend on whether I send the incident wave from the left or from the right, and to tell you where I sent the incident wave from, I'm going to append a small subscript, left or right. Now, it turns out that the outcome of this experiment is completely universal. That means that it doesn't matter at all what I'm scattering on the interface. The portion of the energy which will be reflected and transmitted depends only on one number, which is the C left right, and it doesn't depend at all on the details of the excitation. The excitation can be made out of whatever operators I want. It can have different shapes, different way of smearings, and still the total energy transmitted and the total energy reflected will be one number that is always the same. So that's quite special. You can do some CFT calculation that I will very briefly mention to show that the transmission, in this case, I will focus on, for example, a left coming wave, is simply given by the ratio of this C left right, the coefficient in the 2-point function of the stress tensor over the central charge on the left. And for a right coming wave, it's the same, just C left right over CR. And of course, the reflections are always 1 minus the transmission. Now, ANEC, or that's simply a fancy name for positivity of the energy accumulated at null infinity on both sides, basically just to say that all the energies in the story are positive, tells me that all these transmission and reflections have to be between 0 and 1. And for this to be consistent, since they are somewhat fixed by the same numbers, this means that C left right has to be between 0 and the minimum of the two central charges. And that in turn implies back that the transmissions are always bounded between 0 and the minimum of 1 and the ratio of the central charges. Now, this just looks like equations, but it has a very intuitive interpretation. So of course, I have to transmit something, not less than 0. But the upper limit basically tells me that I cannot fully transmit from a CFT with a higher central charge to a CFT with a lower central charge. I will always have a stronger restriction on my transmission. And the reason is that if I send an excitation toward the CFT that has less degrees of freedom, there are not enough degrees of freedom to carry the perturbation away from the interface. So, yeah, so basically this implies that I will be restricted by just how many degrees of freedom are there on the right to carry the perturbation away. Okay, so just very, very briefly, just to give you a little bit of flavor on how this is proven in CFT, but I will not really go through the details, but just to give a few ingredients, basically what is being done is to build a perturbation that is made out of an operator, which doesn't necessarily have to be primary, but let's call it O left. And this perturbation is basically smeared in the Z and Z bar direction by a function f, which has a fixed width that is not very large. And to begin with, the perturbation is sent at the value of Z bar minus d, so basically at a distance d from the interface. And then it propagates to the interface. Some of it is reflected, some of it is transmitted. The way to measure how much is reflected or transmitted is in terms of these integrals of the stress tensor, full integrals of the stress tensor at null infinity. So these are basically ANEC operators, epsilon r and epsilon bar left. And then the transmission and the reflection are no other than basically 3-point functions in the presence of the interface and their differences in ratio to 3-point functions without the interface. So this can be treated using CFT techniques, and then the result that I showed you earlier can be proven. There are some limitations on this result. So in particular, in the presence of an extended symmetry, if I have other charges, then different charges can scatter differently. There will be more numbers in the theory to play with. And in general, if there are multiple holomorphic quasi-primaries of spin 2, then reflection becomes state dependent. So, okay, so I'm not actually proving it here, but if you want to see the proof, you can go to this paper on the right and see it proven. But what I'm interested in is how to test this or study this in holography. I will tell you exactly why. And that's what I'm going to do next, is I'm going to talk about the holographic model where we have evaluated the reflection and transmission. But maybe I can pause for questions after this part. This is all you need from the CFT perspective. Okay, if there are no questions, then let me move on. So the second part of my talk is about the holographic model that I want to study. That's a thin brain model, basically which generates this defect behavior in the boundary CFT. And it's a very simple bottom-up model, which we use in holography to describe interfaces. So the idea is to consider a thin brain in ADS3. That means that we will have a ADS action which describe the CFT left with certain ADS length L left, which encodes the central charge of the left CFT, and another portion of the action, which is the describing the right CFT, which is basically living below the right boundary in the holographic coordinate, and has a different ADS radius, capturing a different central charge. And then these two chunks of ADS space, the one below the CFT left and the one below the CFT right, would be glued along an interface, which is simply a brain of fixed tension sigma, where the action is just the volume of the brain expressed in terms of the induced metric. Now, in order to find a solution, we want to solve Einstein's equations on the left and right with respect to this action. That's going to give us an ADS patch on the left and an ADS patch on the right with different ADS radii, capturing the different central charges, and a brain basically matching them. To find the location of the brain, we have to solve Israel matching conditions, which are essentially just telling us that the induced metric on the brain has to be continuous when coming from both sides, and that the extrinsic curvature admits a jump, which is of the order of the brain tension. Now, it turns out that these equations can be solved, and one finds stable solution with the brain with induced ADS2 geometry. I didn't say before, but I'm focusing on ADS3 CFT2 because I'm interested in the CFT2 scattering experiment. This solution in general appeared, I mean, it's valid in any dimension. So this, at least in holography, this type of experiment can be carried in general dimensions as well. But here I focus on ADS3 because I'm interested in the specific case of CFT2. So it turns out that stable solution exists with an ADS2 brain as long as the tension is bounded between the sum and the difference of the ADS radii. This can be re-expressed in terms of the central charges. And the solution basically consists, as I said, of two patches of ADS3 connected along an ADS2 brain. The angles at which the ADS2 brain is placed with respect to the geometry are fixed in terms of the tension and the two central charges by this equation. Right, so I should say that this model has been studied like very broadly in holography. Many people were interested in it in various contexts that I will mention in a second. But many things have been calculated, especially with relation to quantum information, so entanglement entropy, boundary or defect entropy, which is the additional contribution to the entanglement entropy for an interval centered around the defect. And this is fixed by the tension, since in this model the tension is the only new parameter. But correlation functions or scattering, which is just another aspect of correlation function, was not evaluated. So why do we want to study scattering in this model? So two reasons, one from the CFT perspective and one from the holographic perspective. From the CFT perspective, we want to have a better understanding of energy reflection and transmission in strongly coupled models with large central charges. Since the result or the bounds, etc., for the reflection and transmissions were all proven with the general CFT, but the holographic CFTs are not general, they are at large central charge and they are strongly coupled. So it's an interesting question to ask whether, for example, we can improve the reflection and transmission bounds when focusing on this class of theories. What can we say about this class of theories? in terms of the reflection and transmission. And another reason why we are interested in that is we would like to understand better the thin brain model in itself. This model has received a lot of attention recently because it serves in double holographic models for evaluating the page curve. So these are models in which people mimic black hole evaporation by a third holographic direction, and the black hole is depicted as if living on this exact type of brain, and the bath where the black hole evaporates to is depicted as the boundary CFT. And you can do all sorts of entanglement calculation using this kind of double holographic model and find that entanglement entropy obeys a page curve, etc. So, so this is a model that people are very interested in, but it's not very well understood. Since it's a bottom-up model, the properties of this model are not very well understood, so we wanted to improve on that. Okay, so that's the model. And now you know exactly where I'm going. So I want to evaluate reflection and transmission in these thin brains. So let me explain how this is, how it's done. I start with the final result because the details are a bit long. So the final result is that the transmission coefficient depends monotonically on the tension and is expressed in the following way. So it's expressed in terms of the 2 ADS radii and the tension. And the higher the tension, so the more rigid the brain in the bulk, the less transmission we have, which sounds quite reasonable. I mentioned earlier that people computed things like boundary or defect entropy in these models, and that was also fixed by the tension. It doesn't mean that always transmission and boundary entropy are the same quantity, or that they are fixed by the same number. It's just because this model is a bit degenerate, it just has one parameter. So it's interesting in general to understand whether transmission of energy and say transmission of entropy or entropy in general are fixed by the same numbers, or if there is a relation between them, under which conditions. But this is just to say that we don't expect it to be in general the case. Okay, so that's the result. You remember that I told you that there is a stable solution in holography for certain values of the tension, certain bounds on the tension. If I plug these bounds into the result for the transmission and reflection, I obtain bounds on the transmission and reflection from holography. These bounds are actually quite similar to what I had earlier from the CFT perspective. So in particular, the upper bound matches the one obtained from the average null energy condition at the beginning of the talk, but the lower bound, which used to be 0, is now stronger. Well, maybe I should say, I forgot to say earlier that this bound that comes from the average null energy condition is actually stronger than the one coming from unitarity or reflection positivity, which those bounds were known before. All right, so I said these are the bounds on the reflection coming to holography. Let's look into them a little bit. So one observation is, as before, that I cannot transmit fully from a higher central charge to a lower central charge. I think this is written flipped. Another observation is that a complete transmission from both sides can only be obtained if the two central charges are the same. And this is also obtained in the limit of a tensionless brain. So that is just what is known as topological interface. And finally, if I want to have total reflection, this is possible just from one side. So if I want to send a wave from the left and have it not pass at all and be completely reflected, this means that the transmission will be 0. That's obtained only if the ratio of the central charges goes to 0. That means that I'm completely depleting one of the CFTs of degrees of freedom relative to the other CFT. It's some sort of boundary CFT limit. But you should notice that what I obtained here in holography, it's very different from what usually happens in CFT. Usually there is no problem to have total reflection just by tuning the boundary conditions and without having to completely kill the degrees of freedom in one of the CFTs. So that's an unusual property of holography, perhaps more generally of large central charges. This we don't know. All right, so now that you know the result, I will tell you the derivation. So the idea is basically to mimic this scattering experiment in the bulk. So how is this done? Start from the boundary. I have a boundary with an incident wave, a reflected wave, and a transmitted wave. These are captured by the stress tensor of the theory, which will be small, a small perturbation over the vacuum with an incident wave coming from the left of a relative size unity, a reflected wave which moves to the left after hitting the boundary with a relative R left coefficient, the reflection coefficient, and a stress tensor on the right which captures the reflection, basically the transmission, sorry, with a relative coefficient T left. And all these waves are going to be monochromatic. I mean, you can probably do more original things, but we started by looking at plane waves with typical frequency omega. The universality that I talked about before, independence of what is sent towards the brain, when I talk about just plane waves, it's just going to be reflected in the fact that the result will be independent of omega, independent of the frequency that I send toward the interface. Just a second. Now, the solution in the bulk in 2 dimensions, once I know the stress tensor on the boundary, is actually completely fixed by a closed formula, which contains the zeroth order, which is just ADS, plus the first correction, which is proportional to the stress tensor, and the second correction, which is proportional to the stress tensor squared, and that's it. So that's an exact solution in the bulk representing these waves. Once I know the stress tensor, I'm going to drag it into the bulk using this relation. And so the only thing which remains to solve for is the placement of the brain. That's the only thing I don't know. So recall that without the metric perturbation, the two sides were matched along a brain with angles theta left and theta right. But with the perturbation, the brain is going to get perturbed a little bit, kind of wiggly, and we want to find its shape. So to do this, I'm going to use coordinates T left, X left, and Z left on the left, and T right, X right, and Z right on the right, and T and Z on the brain. Now, the location of the brain can be described by the value of X, where the brain is placed as a function of those two brain-induced coordinates, T and Z. Maybe not very surprisingly, the time dependence is just exponential of I omega t, as one could easily expect, because it's all the same frequency here. And basically what is left to be fixed is the position of the brain in terms of the coordinate Z, the induced coordinate Z, as I go inside the bulk. Now I also need to fix how to match the coordinates T and X from the left to the right. So generally I would say that the left value of Z is the induced value of Z plus a small correction, and the left or right value of T is the induced value of T plus a small correction. Again, everything exponential in omega. These are 4 more unknown functions, zeta left right and lambda left right, capturing this matching. And of course that it doesn't, the induced coordinates are just a choice of gauge. So the only thing that matters is how does Z or how does a T jump when I move from the left to the right. This will be encoded in the differences of these two functions, lambda left minus lambda right, or zeta left minus zeta right. All right, so I say, encoded the position of the brain or the unknowns about the brain in 6 or more precisely 4 unknown functions of Z. And now I have to write equations for them. These are just the Israel matching equations to fix the position of the brain. I recast the unknown function as, okay, zeta is the difference of the Z matching, lambda is the difference of the T matching, D is the difference of the X positions of the brain, delta left and delta right, and this big delta is some other combination of delta left and delta right. And so I should say these are just 4 functions of interest. These are 6 equations, but it turns out that the equations are redundant due to a momentum constraint. And so I just have 4 equations for these 4 unknown functions on the left. Omega, you know what it is. Z is the holographic coordinate. Theta left and theta right are the angles of the brain, and these I, R, and T are simply factors which contains basically an exponential of C and the angles once again, and they encode the reflection and transmission coefficients. Now, you might wonder, because since these functions delta or lambda were all stripped of an e to the I omega t dependence, you might look at these T's and I's and R and identify that they are hiding some kind of superluminal waves. Because their T and Z dependence is such that they move faster than the speed of light. But this is not really worrisome. The reason that this appears is a little bit what would happen when I send waves going at a certain speed in the direction of the coast. If the waves are very much oriented towards the coast, they will almost hit it instantaneously or at a very, very high effective speed, but this doesn't mean that the waves are actually moving at a very high speed. All right, so I had 4 equations, I will solve them. I start by the homogeneous solution in which I turn off all these I, R, and T, so I'm just talking about vacuum basically, without any scattering experiment. In this case, the 4 functions will be fixed by 3 constants of integration. That's the structure of the equations, A plus and A minus, and a constant D0, which is actually the source of the displacement operator. And for the homogeneous solution, I just want everything to vanish at the boundary. So I want the brain to be straight at the boundary, all the matchings to be trivial. In this case, all the constant of integration vanished. Now, if I add the inhomogeneous part, I get additional contributions, but I can still solve. So I get an explicit dependence of these functions on Z and on the 3 constants of integration. So just to summarize, I solved Israel matching conditions. I have 4 differential equations for the unknown functions and 3 integration constants to be fixed using boundary conditions. And the boundary conditions that I want is basically, again, that my brain is just straight at the boundary. I don't want to perturb my brain at the boundary. I just want this to be a bulk experiment which represents scattering against a straight brain on the boundary. So I can solve these 4 boundary conditions for the 3 integration constants, and I will find something. And the 4th equation will give me a restriction on R left and T left, which should look very familiar. It's the restriction that the reflection plus the transmission sums to unit. But it looks like I completely solved the equations, and still I did not find what is the value of the reflection or the value of the transmission. I just found that everything was consistent. I could fix all the integration constants, and but I wasn't able yet to fix the reflection or the transmission in terms of the Brent tension or the properties of the system. So what is missing? What's missing is something that we often do in holography, is that we need to impose a no outgoing wave condition. It means that there are no waves scrolling from the Poincaré horizon along the brain and back to infinity. So for example, if we focus on the traceless part of the extrinsic curvature, that traceless part of the extrinsic curvature is fixed in terms of the coefficients A plus and A minus. These were 2 of the coefficients that I just fixed by the boundary conditions in the previous slide. And this has an x plus, x minus dependence. So there is one wave that is outgoing. This is the one governed by A plus, and another wave which is ingoing, which is governed by A minus. All right, so I said there should be no outgoing wave, so I should fix A plus to 0, and this finally gives me the result for the transmission in terms of the tension. This was the result that we talked about. So you already know, we analyzed it, we saw that it was increasing with the tension, and sorry, that was decreasing with the tension. We saw that it had some restrictions, like it followed bounds, etc. But one thing that I didn't say earlier, and that is nice to notice, is that despite the fact that we had a parameter omega, which was completely free, the amount of transmitted energy or reflected energy, it doesn't matter, is completely independent of this frequency omega. Within the framework of looking at plane waves, this is the how universality manifests itself. It just means that we don't have different scattering from, for different frequency waves. Okay, so this is basically what I wanted to tell you. Let me summarize and maybe give you a bit of outlook of where I can go with this, like future directions. So we saw that the energy reflection and transmission are completely universal at holographic interfaces in 2 dimensions. In this thin brain model, the transmission is fixed by the tension. Now, in general, well, I said that I could look at this kind of interface entropy, the addition to the entanglement entropy by the presence of the interface. In this specific model, the boundary or interface entropy and the energy transmission is fixed by the same coefficient, which is the brain tension. But in general, we expect them to differ. So it's interesting to try and consider other models which have more than just one parameter to see if in this case the 2 coefficients will differ. Regarding universality, so you saw that what we did was a very minimalistic check of universality, just a check of the independence of the reflection and transmission on the frequency of the incoming wave. One could try to shoot more creative things at the interface, different wave packets, shoot different fields, different scalar, gauge fields, etc., etc., to see what happens in these cases. Is universality respected? Another very interesting question is what happens in higher dimensions. So these proofs that I showed you look like they are specific to the case of 2 dimensions, but the holographic setup is completely general. So one might try to just organize a similar scattering experiment and just see what happens in holography. Is there some sort of universality that is obtained? Maybe not as general as the one in 2D, but maybe still independence of the frequency, etc. And a very interesting last question is under which conditions would there be a relation between the energy and the information transfer? So in particular, in the context of the page curve of black hole evaporation, people are using similar brains to study entropy transmission, how the entropy of the black hole basically disappears into the path, or that might be a too simplistic description, but something along these lines. And so it's very interesting in general to understand what happens with entropy transmission in this kind of interfaces, and is this related to energy transmission, etc. Yeah, and that's basically that's all I wanted to tell you. So there is just a lot of things left to explore in this context, and I hope that I convinced you. So yeah, thanks for listening.
Thank you very much, Shira. Lovely talk. Does anyone have any questions? I know I have a couple.
I have a question if anybody else has. This is Sylvia.
Hey.
Let's go with
Shira.
Sylvia first.
I'm curious about what you were saying at the very end about universality, you know, shooting some extra degrees of freedom on the interface. Mm-hmm. Is that something that you have already thought somehow about it? I mean, could you think of in actually shooting some non-trivial degrees of freedom, some dynamical degrees of freedom with some potential, some non-trivial interaction with the bulk? Or
so I can tell you what we tried. I mean, or trying is more precise. So we are trying with the gauge field, and that seems to be possible. We tried earlier with the scalar, like you would want to, solve the, the scalar in the presence of the brain and see what happens if you turn on a scalar wave and send it in the direction of the brain. There we had a bit of difficulties just because some of the solutions were less nice, less analytic. Yeah. But not that I don't think that we put all our weight against it. So I think there is still stuff to do there.
Okay, thanks.
All right, I believe Andy had the next hand.
Oh, can you hear me?
Yes.
Thanks for the nice talk. I had a few questions. One was that the reflection and transmission were fixed by the coefficients C left right. Is that correct? So, yes. So holographically, did you really need to do a scattering calculation? Couldn't you have just calculated the 2-point function of the stress tensor?
I think you should be able to do it, but since it was not done in this model, I mean, I think maybe we tried and we bumped into some difficulties with some things related to the choice of cutoff near the interface, something like that. I think there is like something weird with cutoffs near the, like when you do a cutoff in a constant value in the Feynman-Graham expansion to, I don't know, evaluate geodesics or things like that. You have some weird stuff happening near the brain that it's not so clear how to fix the cutoff. And I remember that we were kind of puzzled about this, and eventually we just decided to do this through this scattering experiment. But I think it should be possible, and you should recover the same result.
Okay, yeah, I've heard this. I've had the same problems, and so have other people. I think the holographic normalization hasn't been worked out carefully.
Yeah, exactly. But it's a nice way to go around it, right? I mean, if you do the scattering experiment, you know what it should be in the CFT. So in this way, you have now C left right.
Yeah. Also, but then is it surprising that it's independent of frequency, since you know C left right is independent?
No, absolutely not. It's not surprising. I mean, it's basically just the holographic manifestation of this thing that was proven very generally for CFTs.
Okay, and then one last question.
Or I don't know, I mean, maybe it's surprising in CFTs, like, maybe you find it surprising in CFT, like why it's like that. But I mean, just the frequency, it's quite natural, right? Because there is no scale in the problem to fix, I don't know what. It's just independence of scale, the usual independent of scale kind of argument.
Yeah. And you mentioned some bounds on the tension of the brain. Mm-hmm. Could you say what those are and where they come from?
Yes. So you remember, maybe I can even, well, let's see. So can I go back? How do I go back? It's far. Yes, no. very far. Yeah, sorry. So these were these bounds, right? So basically the tension was needed to be between 1 over LR plus 1 over left and the difference. And so maybe I can try to motivate them in the case that the two, I mean, it's a bit degenerate case, so I'm cheating a little bit, but I can motivate them in the case that C left is equal to C right, for example, just to say. And in this case, the upper bound, it gives you an angle of depends how you count it, but like 180 degrees. It means that the brain kind of aligns to be parallel to the CFT left, for example. And then the ADS2 radius diverges. So this is bad. And the other case, it has to do with the false vacuum. So the other case of being bigger than 0, I think they go to angles below 90. It's not really, I'm really cheating when there are two different central charges, but for the same, the angles go below 90 degrees, and this basically means that you have less ADS volume here compared to the vacuum, like vacuum, the one where, I don't know, I put the brain to just touch the CFT right and I feel everything with the CFT left. And so it's basically like a false vacuum kind of question. It's like an unstable local minima that has a higher action than another vacuum that is a competent vacuum. Yeah. So one side it's like the false vacuum story, and the other side it's the tension of this ADS2 brain basically blows up.
Okay, thank you.
And it's the same principles for different central charge, just all these numbers that I said, like 90 degrees, it's not like this, that it works in C left, no.
All right, I believe George had, oh, Andy, were you done with your
I'm done.
Okay, great. I believe George had the next hand.
Yes, okay, thank you. I think you can you hear me?
Yes.
Okay, great. So if I understood correctly, you have two CFTs which you glue along the time direction, and then you extend somehow into the bulk with an ADS brain. So I was wondering, since you know, these top-down models of holographic brains usually have an S2 part or an S part, a spherical part. I was wondering if you could extend into the hologram into the bulk with a sphere, and what would change? I mean, in that case,
I think it's you're maybe giving too much credit to the model, that it's really bottom up, and I don't think we know how to consistently embed it, like get it from a top-down approach. But it's just so simple that people used it so much that I mean, I think it's probably this limit of having a really thin brain, it's probably not, you wouldn't really get it exactly from a good full complete model. Usually like the brain would have like a bit of width in the bulk, and I think it's just you should view it as a very simplistic approximation, that since it's so simple you can still compute a lot of things, so people like it.
Yeah, but maybe yeah, what I was proposing is maybe you can put a S2 instead of a ADS brain, and I was wondering what would change in that case. I don't know, maybe it's easy to do.
But
yes.
So put an S2. I mean,
or an S brain. So no, in S2 it should be an S1 cross R, because we have also the time direction. And then you would, I mean, I was wondering what would change in that case.
So not sure if I understand. So you're saying that I would just extend my full geometry by adding an S1 cross R everywhere? Is that what you would like to do?
Instead of ADS2, yes. You take the time from ADS usually, and then you have an S1, in your case, S1. I don't know if it's an easy to do exercise, but, and I don't know if it's an interesting one. But anyway, I was thinking about that.
Yeah, maybe. But you're saying that this would be better motivated to come from a bottom-up Is it from a top-down approach? Like it's a...
No, both. Well, in ADS is also well motivated.
yeah, I think that's interesting. I don't know how that will work. It's a good question.
All right.
Gerard?
Oh yeah, sorry, I was not clear. You had lower bound on the transmission coefficient.
Right.
Is that in your model or generally true?
The lower bound is in our model, and we don't know if it's a general property of, I don't know, large central charge or strongly interacting, or it's definitely not generally true, because for a free scalar, it's not true.
Oh, okay.
Yeah, the standard lower bound, the one that you get not from holography, is just a 0 here.
Yeah, I was just, so that's okay. It's in your model for some property of your model, which could be.
Yeah, it could be completely specific to this model or to a class of models which contains this model, but it's definitely not general. You know that it's not general because this lower bound, it told you that 0 reflection forced you to turn off one of the sides, completely turn off the degrees of freedom on one of the sides, and you definitely know that's not true. So for example, I can organize, you know, 2 boundary CFT, I just put them together,
Yeah.
not talking at all, and there is no problem with that, right? So.
Okay, thanks very much. It's very nice talk. Thank you.
Thanks.
Okay, so we are just about at the end. Maybe I'll abuse my privileges as organizer to ask one more question, and then we'll have a short break before reconvening in about 37 minutes or so. So my question was, well, Andy asked one of my questions about C left right here and its status in the thin brain model. The other question, you know, one way at arriving at the solutions that you were writing down for stress tensor fluctuations in the absence of the interface is just solving the conservation equations up to boundary conditions at infinity. That's enough to give you the you know, null fluctuations that you found upon applying that, you know, stress tensor is traceless. And I was wondering if there's some way, some sort of how to say, of souping this up. You consider the word identities in the presence of the interface. So with the extra delta function terms that come from broken translations. And if you know how much of this business of these energy perturbations just comes from solving the word identities in the presence of the interface.
This is a question in the CFT side.
Yeah, just purely in CFT terms.
Yes, it definitely comes from the word identities. Well, one incarnation of the word identities is in this all the fixed 3-point functions, right? But I don't know. So I know that if you do the usual manipulations that you do to try and get the word identities, it's really quite a bit black magic, the fact that you get all the 3-point functions, but not all the 4-point functions. So the point is that when you do the word identities, right, usually there are these recursion relations that follow, right, that give you correlation functions of stress tensors in terms of derivatives and stuff of one stress tensor lower. But in the case of the defect, it doesn't, so it's, for the boundary, it still works. And for the case of the defect, it works like a flip, like a folded boundary. So it fixes all the correlation functions of something like T left plus T bar right, and all the correlation functions of T right plus T bar left, and between them and everything.
But I think I'm asking something much simpler than endpoint functions of the stress tensor in this scenario. I'm just saying, you know, the 1-point function of the stress tensor in a general state is constrained by the word identity.
Right.
So for instance, and if we're just considering just CFT, no interface, then, you know, stress tensor is conserved and stress tensor is traceless.
Right.
And that's enough to see, you know, these non-dispersing fluctuations that one has in just ordinary CFT. I'm just referring to, you know, solving the word identity for the 1-point function in basically in vacuum with the interface. Like you treat it as a differential equation that constrains the behavior of the stress tensor. But it seems that you guys haven't thought about this, so maybe it's a bit
Oh yeah,
unfair.
sorry. No, it's okay. It's interesting, but I don't know. I don't have something.
You have some
insightful to
universal
say.
results within the context of these models, which raises the prospect of giving a universal analysis purely based on CFT word identities
No, but
rather
no,
than
no.
holographic
Sorry.
data.
I don't know if this was clear. Like the results that I presented in CFT was completely general, just was not done by us. It was done by
Right.
3 other people: Joao Penedones, Marco Maineri, and another guy that I don't remember the name. And their proof is coming from the CFT basic principles, basically, and they proved this result to be completely general, or not completely general, general within the caveats that I mentioned at the beginning, that you don't have additional extended symmetries, etc., etc. But we just did this calculation inside the holography.
Right. You effectively computed the C left right inside of this model.
Exactly.
Yeah. Their computation, they were dealing with I guess 3-point function of or sort of the 3-point function of stress tensor with 2 other operators.
Sorry, can you say again, because I got disconnected for like a very short moment, and then I lost the beginning of your sentence.
Their proof. So they're looking at these ratios of stress tensor in some certain state and normalization of that state. So they're looking at some 3-point functions. Is that right?
Yes.
Okay. I guess I'm advocating that there may be a simpler proof of simpler version of their proof.
I see. And this by somehow adding the defect as a delta function or something like that.
Mm-hmm. Yeah, the word identities, the things that get modified in the presence of the interface. Thank you very much.
It sounds very interesting. I mean, I haven't thought about that, but I mean, I'm happy to talk more to understand exactly like what, the idea that you, like how you have in mind. Now we cannot hear, or I cannot hear you anymore, but maybe you can, the problem is with me.
Maybe with the earpiece.
Yeah, now it works. Now
Okay.
it's works.
Maybe we can chat during the break. Thank you very much again for the talk. We should all thank Shira again, and we'll have a break for about half an hour or so before Ananda Roy will speak.